So let's say you're cooking some meat, right? Today I cooked pork actually, and I got it out of my fridge. It was kind of red. Same thing with beef or other types of meat, lamb. And so you put it on the stove and it starts to turn brown, right? Why does it do that? Also, just out of curiosity, why would perhaps a whale be able to stay underwater in the deep sea for hours on end without having to come up and grasp for air? Well, these things can actually be explained by hemoglobin and myoglobin, which we're going to be talking about and comparing today. So, whether you're just curious or you're studying for a class, I hope you find this video helpful, and I hope you know how much you're loved by the creator of our great and beautiful universe. So without further ado, let's start talking about hemoglobin and myoglobin. If we talk about myoglobin first, so let's go back down to the very basics and beginnings. We're made up of a bunch of proteins, right? Not just proteins, but we do have a lot of proteins in our body, and hemoglobin and myoglobin are made of proteins themselves. These proteins in specific, and we're going to talk about their structure, are able to carry what we call oxygen, right? And these hemoglobin and myoglobin are how we basically get oxygen delivered to the rest of our body. Okay, so how does that work? Well, basically, myoglobin is great for storage. The storage of oxygen. That's one thing you should remember. The storage of O2. In, myoglobin, think muscles, right? So myoglobin, we have it in our muscles, and it's good for the storage of oxygen. Then we have hemoglobin, and hemoglobin also has oxygen. Remember, both of these proteins, both of these molecules carry oxygen and try to provide oxygen to the rest of our body and cells that need oxygen. But hemoglobin is better at transporting oxygen, not necessarily storing oxygen, but it's much better fit for transporting oxygen. And hemoglobin you can actually find in the red blood cells, like in your bloodstream. So, okay, let's go back to the big picture, right? I accidentally cut myself, right? Let's say that I do. That red blood that I see on my finger, has tons and hundreds of hemoglobin, I'd say thousands of hemoglobin cells, little tiny red blood cells. Like if you were to search a red blood cell, this is what we're talking about. Those are hemoglobin cells, are red blood cells, and they're great for transporting oxygen. Versus myoglobin, you would find in your muscles, and it's, like I said, great for storing O2. So let's go back to the cooking, right? Back to the cooking scenario. Usually we cook muscles of animals, like we cook a steak, or we cook with that type of meat, with any type of meat. The change in color is actually due to a change in oxidation state in the meat. Okay, so now we gotta get more into the structure. What do I mean by oxidation state? Specifically, what do we mean about the change of the state in the iron in our blood, in these molecules? So if we talk about that, I'm going to put in this middle column what they both have. Both of these have iron. Both hemoglobin and myoglobin have iron 2+. So if you go back to Gen Chem, you'll remember that's its oxidation state, 2+. And whenever you're cooking in meat, you're going to get something you're going to basically turn that iron molecule in the middle of your hemoglobin into iron 3+. Okay? That means you're losing an electron, right? Because in order to go from 2+ to 3+, you have to lose a negative charge, going back to Gen Chem. So whenever you're cooking, the reason why your meat changes colors is it goes from this being able to contain and hold oxygen, myoglobin, store oxygen in myoglobin, to all of a sudden I can't do that. I'm losing all these electrons. My protein is being denatured. Denatured means it's kind of being deactivated. It's being kind of, the protein is being unfolded. It's changing its structure, its shape to where it's no longer going to work again. And so that part of that is losing an electron of your iron molecule going from iron 3 plus to iron 2 plus, and that's what's going to cause the cooking of your meat. So I think that it's really important to remember that hemoglobin and myoglobin both have in their structure iron 2 plus. That's really important because how this whole thing works, basically, if we're going to let's go to the basic subunit of what we're talking about with hemoglobin and myoglobin, although they are a little different. Basically, what you're going to have is you're going to have this tertiary structure of protein. It's going to be 8 alpha helices. So remember an alpha helice. What is an alpha helice? Just a quick recap, alpha helices is a type of secondary protein structures. So we have 4 different types of protein structures, and we're talking about our secondary structure out of the 4, and we basically have 8 alpha helices of these. So think about like those big coily things that you can search up. If you search up hemoglobin, you're going to see like these coily things, and those are your alpha helices. But so we would actually label these alpha helices A through H. That's a little detail. I'm not sure how detailed if you're studying for a test, your professor will be, but that is something to keep in mind. So 8 alpha helices in one, let's call it a molecule. So I'm just going to draw like this molecule thing. Pretend that this is all of the alpha helices combined in this molecule. Okay? Versus hemoglobin, it's what we call a tetramer. Yes, tetramer. I'm pretty sure that's how you say it. Tetramer. And if you think about the Latin root tetra, this basically means 4. So imagine 4 of these. It's very similar to myoglobin in its structure. Imagine 4 of these myoglobin structures combined, and they're all sticking next to each other. They all make one hemoglobin molecule. Yeah, these 4 hemoglobin subunits, which resemble one myoglobin subunit, and that's kind of like the structure that we're looking at. So imagine we took myoglobin, and it's a very similar structure for hemoglobin, and we just multiplied by 4 and combine that into 1. That's our hemoglobin molecule. So myoglobin is a monomer. Mono means 1, myoglobin monomer. Hemoglobin is a tetramer. Tetra is 4. It's like 4 of these molecules, but together they make 1 molecule. It's like 4 myoglobin molecules, but hemoglobin has the 4 subunits, and the 4 subunits make 1 molecule. Does it make sense? 4 subunits. Okay? So the way that we would break up hemoglobin is we would break it up like this. 2 alpha and 2 beta subunits. So we would say beta 1, beta 2, alpha 1, alpha 2. And that's basically how we would just change our subunits. Basically, scientists just name these subunits, right, for hemoglobin. And then remember, these are folded proteins. They have an N-terminus and a C-terminus in them, but they're folded in different shapes, these like squiggly lines kind of things, and making these structures that we're dealing with. So now we're going back to the beginning. How are like whales able to stay underwater for so long, and why is this iron oxidation important? Well, in order for oxygen to get into, there's like this little pocket inside of myoglobin and hemoglobin where the oxygen can bind, but it has to go through this whole process in order to get there. Going back to the amino acids, right? The specifically organic amino acids, right? We got 20 of them. Remember histidine, right? Think about histidine is actually really important. Distal histidine on the top of this, like here, let me draw one of these subunits for you. We have like this histidine thing, or histidine kind of has like this. And your subunit is like all of these beta kind of things, like this. And so you kind of got like this gap in the middle right here, where you got a histidine sticking up and histidine sticking down. And this little gap right here that I'm going to draw in blue, this little gap, you could potentially put an oxygen, an O2 molecule there. O2 being, you know, 2 oxygen molecules actually combined together. You could potentially fit an O2 right there. But the regular default is you actually have an iron right here. You would have an iron 2+. If you have an iron 2+ in this section, your meat's not cooked. Your meat could have oxygen in it, right? But if you have an iron 3+ in it, like you were talking about, your meat becomes cooked, you lose that electron, you actually cannot have any more oxygen bind into your molecule. You can't. So hemoglobin and myoglobin can only have an oxygen in there and do their job of transporting oxygen and all that if we have an iron 2+, not iron 3+. Okay, so we have a distal histidine and we have a proximal histidine at the bottom. And we also have, I can probably make another video going into more of the specifics of this, because we do also have other amino acids highly important in this process. Specifically, this is histidine 7, and then this is histidine 8. When we have amino acids in the body, they're named. We have like the serine proteinase mechanism, we've got all these different things that I'll be going over, so look out for my new videos, but in case you're interested. But we always have our amino acids named. So histidine 7 and then histidine 8 is our proximal, and histidine 7 for our distal histidines. So basically, you kind of have this structure where it's kind of like locked in. If there's high CO2 concentrations, carbon dioxide concentrations, if the body isn't getting enough oxygen, you have this locked in state. But let's say that your blood goes to your lungs, right? And there's an increase in oxygen, then after some pushing, the oxygen is able to squeeze in and kind of like moves, and it turns your whole protein about 15 degrees. And that is just enough for the oxygen to fit in, to bind with the iron, and this 15-degree turning mechanism will actually then affect the rest of the subunits for hemoglobin. For myoglobin, you get it in once, you're good. It's only one subunit. But for hemoglobin, it is something called cooperative, or cooperativity, or allosteric. And anyways, if you're able to get one oxygen in there, it's harder to get in there, but if you're able to do it, then it's going to change the structure of all of the subunits. Kind of like this cascading effect, kind of like this domino effect. It's going to make it a lot easier, and this is called allosteric cooperativity. And in a different video, I'll go into the difference between allosteric inhibitors and cooperative activators and that kind of stuff, and what we're talking about the Bohr effect, and we're talking about chlorine in there. So look out for that, but that'll be a different video. Right now, we're just talking about the main differences between hemoglobin and myoglobin and the structures. And so hemoglobin, if you're able to get one oxygen in there, it's going to cause this effect for all of the other subunits, an easier process with that. And so let's compare really fast these two curves, which are used to describe these two situations in these two molecules. So another thing to remember is that it is reversible, right? Once an oxygen gets in there, it's not stuck in there forever. The oxygen is going to go through the bloodstream, it's going to travel through the bloodstream, and then it's going to release that oxygen to wherever it needs to go. Going back to the whale thing really fast. So I hope this explains a little bit more now on how whales are able to stay underwater for so long. It's because once they're locked into that myoglobin, that the oxygen's locked into the myoglobin, it can stay there for a long time until it's needed. Myoglobin, it's a lot easier for oxygen to get into that one subunit. Hemoglobin, it's not. So now let's get into the charts. So this is what your chart is going to look like for if we wanted to demonstrate kind of like the functioning of how easy it is for oxygen to bind inside of a molecule. And so we would call this a hyperbolic binding curve. Affinity means how likely something is to bind. So on our bottom, we're going to have PO2, and that basically just means the partial pressure of oxygen. And we have our YO2 on the bottom and the top. Okay. Basically what you need to know is just what these curves look like. So for myoglobin, like I said, it's a lot easier for the oxygen to get into this one subunit. Myoglobin, therefore, has a high affinity. This means it's equivalent to having, it binds really easily. Oxygen, the molecule, binds really easily into a subunit. It just does, and it stays there really well. That's why myoglobin is good for storage. So our myoglobin binding curve is going to look like this. This is called a hyperbola. It's going to look like a hyperbolic curve. And basically means that you just like need a little bit of an oxygen concentration, and it's going to go through the roof. It's going to do its job. It's going to bind really fast and quickly. And so that's really important to remember. I can probably make another video going into more depth of how to read and work with these curves, because these curves, there are a few calculations, and it's also important to remember that they're the half saturation points. The half saturation points are really are numbers that you might be tested on. For example, for myoglobin, your half saturation point is 2.8. And there's a whole equation on how to get there, 2.8 torr specifically, because we're talking about pressure. But we can talk about that later. Just like I said, for this video, we're comparing the two. For hemoglobin, we have something called a sigmoidal curve. Because remember, I said it's harder for hemoglobin to bind initially inside of this molecule. But once it does a lot better with getting new oxygen molecules able to bind into these 4 subunits. So what do I mean? Okay, let's take one subunit for example. Beta 1, right? Oxygen has a hard time binding in it. Okay, and it's like kind of hard to break this structure, right? So it's going to be a slower kind of like curve compared to this one. It's not going to go. It doesn't have a high affinity like myoglobin does. But let's say that oxygen does, O2 does get into this. It's going to cause that effect that's going to make it a lot easier for 2 more oxygen molecules to go into beta 2 subunit. And once that happens, it's going to be a lot easier for 2 more oxygen molecules to go into alpha 2 subunit, the alpha 2 subunit, and then even easier, right, for 2 oxygen molecules to go into this last subunit, alpha subunit. And like I said, this is due to cooperativity, basically. So you're having trouble, right, getting in there, but then you are able to get in there, and then you kind of have this like turn away shift. And as you can see, this kind of makes like an S shape. This is called a sigmoidal curve. So hemoglobin has a sigmoidal curve when you're talking about its affinity, right? How well it binds, how well oxygen binds. And your your halfway point is going to actually be 26. That's where your halfway point is going to be, 26 torr. So that's going to be your important number for that. It's kind of like this whole process of how these things work. Sometimes I've seen it go both ways. That distal H7 could be at the bottom, and the histidine H8 could be at the top. Also, another important thing that you might be tested on is both of these are connected to valine E11, especially when we're talking about the T state versus the R state. But that will be another video. It's very similar. It's very interconnected to what we're already talking about. T state means tense state, so that's when it's not being binded to with oxygen. And R state means relaxed state, when it is in fact open enough, or it's changed its angle enough, 15 degrees, remember, for an oxygen to bind in there. Remember, T state is tense state, right? No oxygen binding very easily. relaxed state, R state, is when you actually have an oxygen in there, and it allows for cooperativity, right? Us going and adding, allowing more oxygen to get into those different subunits. And it's the same thing for myoglobin. They both have T state and R state. Just remember, one has cooperativity and the other doesn't. Why? Because one has these subunits where they can cooperate with each other, and it's kind of like cascading effect, while the other one doesn't. So let me just write really fast here. Cooperativity, and right here, T versus R state. T equals tense state, and then R equals relaxed. So this was kind of just an intro into hemoglobin versus myoglobin. There's a lot more details to come, so keep your eyes out open for another video. But I hope this helped. I hope this made a general overview sense, and I hope this now explains how whales are able to stay so long underwater, because they're in the R state. They have oxygens in their muscles, and unless there's something that causes oxygen to be released, which basically is there's not enough oxygen in the blood or in the muscles, unless there's something that causes that to be needed, it's just great. Myoglobin's great for storage, versus hemoglobin is like in our red blood cells that travel all over the place. And so whenever there's a high affinity, like a lot of oxygen saturation, it's going to open up, it's going to take an oxygen, then it's going to go to the body where there's less oxygen. It's going to see that there's less oxygen there. It's going to be like, okay, we actually have low affinity now, because we're going to release our oxygen. We're going to go back into the tense state, and that's when that's how oxygen gets spread into your body, which is really cool in my opinion. There's a lot of, that's the basic science around how your body gets blood everywhere, and I hope you found this interesting, helpful, and I hope you remember how much, you're loved by the creator of the universe. Thanks for watching. Bye.